First, we will discuss about ECG and power line. Power line is required for our device, but at the same time, power line is a big problem for our amplifier system. You can see in this figure, we have a patient here and a device, an electrocardiograph device here, a power line here, and we want to consider the bad effect of power line on the also our device and our leads, as you can see here. These capacitance are some stray capacitances. As I mentioned before in the previous lectures, if we have two conductor power line and the wires and dielectric between them, we have capacitive behavior. We don't have any real capacitances here. C1, C2, and C3 are the model of the capacitive behavior of the environment. But these model capacitances affect on our system, affect on our wires, and therefore we should model these bad effects. As you can see, because of the C1, we have a current ID1 here, and because of C2 we have ID2 here. In common mode problems, we assume that our body acts like a single node here. And if I draw the simplified electric model, you will have something like this. We have a power line here, C1, C2, ID1 and ID2. These currents flow through our body and our body will act like a node. Let me draw the impedance first. As you can see, Z1 and Z2, and now we reach to the body node. These currents ID1 and ID2 will be collected in the body and will flow through ZG ground impedance to the ground. And VA and VB in our lumped electric model are located here. VA and VB. Let's write the exact VA voltage first. VA is Z1 multiplied by ID1 plus ZG multiplied by I, this current. And VB also is Z2 multiplied by ID2 plus ZG multiplied by I. Therefore, VA minus VB here can be written as this. ID1 multiplied by Z1 minus ID2 multiplied by Z2. And if we assume that ID1 and ID2 are as the same, Hunter and Webster have shown this claim. We can assume this equality. Now we can rewrite this difference voltage between VA and VB as this simple term. Okay, as you can see, we have a voltage dropped on VA and VB, the input terminals of our amplifier, of our device, because of the power line bad effect, because of the power line interference. And as you can see, if we want this bad effect, this interference goes to 0, we need to minimize or zero this voltage. We should try to minimize, and the minimum voltage of the right hand of this equality, this equation, is 0. And for zeroing this value, it's enough to have same impedance Z1 and Z2. Z1 and Z2 is the total Z1, and each of Z1 and Z2 is a total impedance related to the wire and the electrode and the skin of the recording location. Therefore, having same situation of recording in every recording location is important to remove the bad effect or remove the interference because of the power line. If we remove this bad effect, we have a clear signal, as you can see here, and this part of the recorded signal, for example, is affected by the bad interference from the power line. As I told you before, all currents flow from the power line, from the connected leads through the body and ground impedance, and also our body acts like a single node. In this slide, we will consider the leakage current from the power line to the body. As you can see, directly the current flows through the body, and also we have a stray capacitance here, CB, and we have a current IDB. We should consider the voltage dropped on the input terminals of the amplifier. Okay, let me to write the common voltage dropped over the body, because the current will flow through the body and the input impedance of the system Zin is high. Therefore, all the current will be flow through the Zg, and the common voltage of the body is only based on the drop voltage on the Zg. We have a current IDB, common node, single node of our body, and also Zg and the ground. And we have two connected lead, Z1 and Z2, also Z2 a high Zin impedance, and VB, and also we have Zin here and VA. Okay, first of all, we should calculate the voltage VCM, common mode voltage, on the body. And as you can see, because of the high impedance Zin, we don't have any current flow to Z1 and Z2 through Z1 and Z2, and all the IDB will flow through Zg, and common mode voltage can be calculated but by the simple by this simple IDB multiplied by Zg. And also we should write the VA and VB. VA and VB is a voltage dividing by Z1 and Zin and Z2 and Zin. VA is Zin divided by Zin plus Z1 multiplied by VCM, and VB is Zin divided by Zin plus Z2 multiplied by V common mode. Therefore, the difference between VA and VB can be rewritten as this equation. And because Z1 and Z2 are much less than Zin, you can find the difference VA minus VB as this simple term, V common mode multiplied by Z2 minus Z1 divided by Zin. For zeroing the bad interference voltage VA minus VB, which is dropped on the input terminals of our amplifier, we only have one choice. We should provide a situation to have same Z at our leads. We should have same impedance on our leads. As I told you before, Z1 and Z2, each of Z1 and Z2 is related to the wire, to the electrode, and also the skin impedance of every recording location. Therefore, if Z1 equals Z2, based on this equation, VA minus VB will be 0. And this is a good situation. But if we use different electrodes on each hand here, Z1 and Z2 will not be as the same. Therefore, we will have bad interference on our input terminals of the op-amp.